Okay, kids, we're back, and now we're going to look mathematically, come up with an equation and everything for something we studied in grade 11. You may remember in grade 11 I had a magnet, and then I had a wire with a current going through it. And when the wire had no current going through it, there was no magnetic force on the wire. Then all of a sudden we turned on the current and the wire moved. Now the wire either moved up or down depending on the direction of the magnetic field and the direction of the current. Now if you don't remember this, I have found another physics teacher or another professor, I don't know who the gentleman is, but he does a good job of it. It's very similar to what we did in our class in grade 11. And you might want to stop the video now, go to the link for this magnetic force video that I've left for you in today's announcement. Go there. Take a look at it. It's a good way of reminding you of what we did in grade 11. And then come back and we'll pick up with today's lesson. Okay, so why don't we do that? Why don't we take a look at that video I posted? Some nice gentleman doing some physics for us. And we'll be back. All right, I hope you watched that video because it should remind you that the force magnetic, you get its direction from the right hand rule. If you remember, if you get your right hand out and you have an open hand, don't curl your hand or anything. It's an open hand. There's your thumb. One, two, three. I think you stop there if you're Homer Simpson. Right there. Okay, so your hand is open. Right hand. And you point your fingertips in the direction of the magnetic field. So in this diagram, the magnetic field goes from left to right, from north to south. So your fingertips of your open hand have to point that way. Your thumb has to point in the direction of the current. Now look, the current is a circle with a dot. See that? That means the current, and this is positive conventional current, not electron flow. We went over this in grade 11. Positive conventional current, which flows from the positive end of a power supply to the negative end. This positive conventional current is coming out of the page. So your thumb has to be pointing in the direction of the dot out of the page. And look where your palm is. Your palm is up the page. So that's where your force magnetic would be. So that's how we get the direction out of this right hand rule. So this is what I want us to do. I want us to consider the current that's in this wire. Okay. Now, this is an end view, a cross-sectional view. I want you to consider the current to be a set of individual moving charges. So think about all the individual moving charges that are in this wire. All right, so this is a side view right here. A top view would be like this, right? Here's N, here's S, north and south seeking pole. There's the wire. We're now looking at the top view of the wire, and there's the current. So this is side view, this is top view. So in here where the magnetic field exists, consider the current to be a set of individual moving charges. Well, oh my goodness, I learned about this yesterday. I can find the force magnetic on each individual charge. And the force magnetic is equal to the charge on each individual charge, how fast each individual charge, cross product the magnetic field. Now, the magnetic field and the direction of current and the direction of charge motion is perpendicular, right? Magnetic field is left to right. The current is coming out of the page, so that's 90 degrees. So I can get the magnitude of this magnetic force. I can get its magnitude, and it would be the magnitude of the charge, magnitude of the velocity that the charged particles are moving in, the magnitude of the magnetic field times sine of the angle between them, but it's 90 degrees, and last time I checked, the sine of 90 was 1. So force magnetic becomes QVB, all magnitudes. All right, let's continue with our discussion. And I'm going to have a let statement here. Let there be n forces and the number of charge that pass through B in time t. So what what we're saying here is in a certain amount of time t, let n particles, charged particles, flow through here. Flow through where? Flow through this confined area where the magnetic field exists. We're going to simplify this and say the magnetic field only exists in here, confined in here. And we're going to say in a certain amount of time, let n charged particles flow through here. So that means the magnetic force would equal the magnetic force on an individual particle. Each particle has this force on it, but there's n of them. So the total magnetic force becomes n times the charge on each one. All right. Then what we're going to do is we're going to multiply top and bottom by the number of charges that pass through where the magnetic field exists in a time t. It doesn't change anything. If I multiply the numerator and the denominator by the same thing, I haven't changed the quantity. But what it does do is it makes us realize that if you multiply how fast something is moving by how much time it is moving, you get a distance. V times t gives us a distance. Well, in this case, V times the time in here is this distance. It's L, the distance from one end of the magnetic field to the other. Speed times multiplied by time is equal to distance. In this case, the particular distance is L. So I'm going to get rid of this V times T. I'm going to get rid of this V times T, right? And I'm going to give myself an L. It's going to be an L. The other thing you're going to realize is all the way back to grade 11, that current is equal to how much charge passes through a wire in a certain amount of time. Q over T. Well, look, how much current, N times each individual current, divided by T, excuse me, N times each individual charge, gives us the same numerator here. Look, big Q is how much charge goes by. Well, look, N times each individual Q gives us that charge divided by time. And this whole term here, NQ over T, is the same as big Q over T, which is the current. So a couple of grade 11 concepts there. So NQ over T gives me I. Speed times times gives me L. And we have a new equation that the magnetic force magnitude equals the current times, for what length is that wire exposed to a magnetic field, L, times the magnitude of that magnetic field. And if we want to take a look at this, we can see that since this is a magnitude equation, this would be its corresponding vector equation. Force magnetic in newtons is equal to current in amperes multiplied by the length that the wire is exposed to the magnetic field in meters, cross product the magnetic field which is in Tesla. So this is the current in a wire version of this. Which is the magnetic force on an individual charged particle. We use this one. When it's particles moving in a wire, we use this one. All right, let's do an example. Let's say you got a north-seeking pole of a magnet here, south-seeking pole of a magnet here. Let's say the magnets are L meters wide. Okay, that tells us how wide the magnetic field is. And let's say that it's 0.12 meters. That's what our L is. And let's say that the current is in a wire that goes through this area where the magnetic field, so this is a top view, all right, top view. And there's 30 amps going through that wire. That's quite a bit of current. Right? You would not find 30 amps in a house. Well, maybe on a stove or an electric stove or an electric dryer. That's about the only place. Most times, most wires in your house, they cap out at 15 amps. But maybe for those heavy duty equipment, you might have 30 amps. You probably would. And let's say that the magnetic field here, which goes from left to right, I've drawn it in purple here. Let's say that that magnetic field is 0.90 Tesla, goes from left to right. And that there's an angle between the current and the magnetic field. There's an angle here between the current and the magnetic field, and it's shown as theta in here, and theta is 60 degrees. So what would be the direction of the magnetic force? Well, you use your right-hand rule. You use your right-hand rule, right? And I hope you realize that if you use your right-hand rule on the current, you'll see that the current has a portion, right, that's parallel and a portion that's perpendicular to the magnetic field. Well, we're going to ignore the portion that's parallel because if you have a current which is parallel to the magnetic field, you don't get any force out of that. If you get a portion of the current which is 90 degrees to the magnetic field, you get maximum force. So let's deal with the portion that's perpendicular, all right? So we got the magnetic field. Get our right hand out, open right hand. Magnetic field is going left to right. It's in purple, so get your hand pointing in that direction. Your thumb's going to point upward to take into account the perpendicular portion of the current. Look where your palm is. Your palm should be facing towards the screen. So your thumb is up towards your ceiling. Your open fingertips point from left to right. Your palm should be facing towards the screen. And we draw that right here. The direction of the force magnetic. Circle with an X, meaning into the screen. So we've done the direction part. Now let's calculate the magnitude of the magnetic force on that wire. So it's how much current, for what distance is the current exposed to the magnetic field, how much magnetic field, and the sine of the angle between them. So there you have it. Plug it all in, you get 2.8 newtons. Then you combine the magnitude and the direction, you combine them, and you get your final answer. 2.8 newtons into the screen, into the page. So today's lesson is almost a year in the waiting since I first showed you this demonstration in grade 11. I didn't give you this equation. Grade 11 mathematics was all qualitative, really. Now here's the quantitative part of it. And what's really cool is it's just an extension of the magnetic force on an individual moving charged particle in a magnetic field. We just consider a current to be a whole bunch of charges confined to a certain area of exposure or certain length of exposure to a magnetic field. So today we got this lesson, we got the video you can watch, other links there, a note, some questions to do. I hope you have a great day, and we'll talk to you soon. Bye-bye.